Hi, this is Crossdot and Nabla, and this is now on our Chapter 12 section of Calculus 3, where we'll be covering over functions of several variables. And in this first section, we'll be covering over planes and surfaces. This is kind of like the foundation of this chapter, right? And the most basic example of this is just going to be the plane. What is a plane, right? If you've taken any algebra class, you can remember what a plane looks like, right? This is the xy plane, pretty straightforward. However, in Calculus 3, we've extended this to several variables. Now we're in the x, y, and z plane. This is a little bit different than before, where we had only 2 dimensions to worry about. Now we have that third one to consider, and that leads to a lot of different types of ideas and equations that go along with it, right? And this first point right here, equations in 2 variables. This is kind of what we think about like standard form stuff, right? We have something like ax plus by equals c. And that's just your standard form of a linear equation, right? So if you have some sort of arbitrary curve that meets that, right? You can solve for the slope of it, you can solve for the y-intercept, you can solve for the x-intercept, you can solve for all the different characteristics of that line. However, in 3 dimensions, a plane is the 3-dimensional version of a line, right? And we can just say that a plane is just equal to, let's not use, right, let's use y, ax plus by plus cz equals d. And you just go in alphabetical order for that. The constants don't matter as much as the variables do. In this case, in algebra, we often set, in algebra 1, algebra 2, we often set that z to be 0. So if we just set z equal to 0, you get a line. But in Calculus 3, z, like x and y, are going to vary, which allows the creation and graphing of these planes, right? And we have a more technical definition of what a plane is. So you're given a fixed point, p naught, a non-zero normal vector. We covered that in our last section, the normal vector. It's going to be pointing up and outward. So in this example right here, this is pointing up and outward from the point, right? For the sets of p, for the set of points p in R cubed, this is just 3D, for which p naught p is orthogonal. This is a vector. It's orthogonal to n. It's called a plane. You have to derive this relationship. A couple things to note with this derivation. It's going to be a cheeky one, actually. What you're going to use is, we know that the normal vector, this is the normal vector, and this plane, not this plane, this vector right here, p naught p, are orthogonal to each other. And we have a little friend from an earlier section that we used. Whenever we have something that's orthogonal, we can do something with that. We can use the dot product operator, right? So we can say that n dot p naught p equals ABC. Again, ABC is completely arbitrary. And then we have x minus x naught, y minus y naught, z minus z naught. And then this is all going to equal 0 because this is going to be a cosine of 90. And if you have cosine of 90, that's going to be equal to 0, right? And that's the beauty of this dot product equation. We can actually use it to now solve for this, solve for the expression for a plane like we just did above. So then we have a plus times that quantity, b times that quantity, and then c times that quantity, all equal to 0. How awesome. And now we go on to example 2, where we're given a plane through 3 points, and you're trying to find the equation of the plane that passes through these points, P, Q, and R. And our normal vector is actually going to require another operation for vectors that we've seen before as well. It's the cross product, right? And we've actually added up vectors before, or gotten vectors from different points in space, and this and that. This isn't supposed to be a difficult problem. This is supposed to be a problem applying what we just learned above in page 1 to generalize it, to generalize this, right? So feel free to pause the video and try this one on your own. Let's jump right into it. So I'll just choose PQ and PR because, yeah, that's what I prefer to do. I always have to go right to left, so it's going to be Q minus P. So it's going to be -3. So the vector is going to be -3 because it's going to be 0 minus 3. 4 minus -1 is going to be 3. And then, wait. Let me just check again. So it's going to be, oh, no, I flipped the order. Sorry, oops. -1, -1, 5, -3. There you go. I got myself mixed up for a second. Okay. And then R minus P, so it's going to be 0 minus 2. So -2. -1 minus -1, it's going to be 0. 5 minus 3 is 2. And then you take the cross product of these because you want the normal vector between these two, and that points upward, right? In this example right here, this is always going to point upward, not point upward, point outward from the plane orthogonal, point orthogonal to the plane, right? That's going to be the whole point of that operation, right? And then we can just get into our cross product right here. This should be pretty straightforward. If you have a calculator, you can just, if you have a TI Nspire, actually, you can just plug it in there. I'm going to do this by hand, the old-fashioned way. So we got 10 I hat plus 8 J hat plus 10 K hat. And we can rewrite this as our good old vector operation like this. And we can also just scale this down because there's a constant of 2 in there. Just going to make our lives easier, right? Now we have our A, B, and C, like we had above here. We have our normal vector now. We want our point. We can choose any point, honestly, it doesn't matter. I might just choose point P. It makes my life a little bit easier to do. So it's going to be 5 times x minus 2 plus 4 times y plus 1 plus 5 times z minus 3 equals 0. And you could have chosen P, Q, or R. It doesn't matter. You're still going to get the same result. 5x minus 10. So I'll just do 5x minus 10 plus 4y plus 4 plus 5z minus 15 equals 0. So 25, 21. Yeah, and then we're going to get this as our result, as our plane in space. And if you were to actually go on Desmos and plot all these points, it would work out. And you can just plug in check P, Q, and R into this and see if it satisfies the equation, right? Example 3 goes a little bit more into the technical stuff, like the rules and properties of it, right? Given what we know now, you want to try this on your own, feel free to pause the video. So let's jump right into it. Finding a vector normal to Q, nice little shortcut. We know that this is just each of the x, y, and z components. So A is just going to be, just call that n, like that. Perfect. B, find the points at which Q intersects the coordinate axis and plot Q. Okay, this is going to require a little bit more precision than part A, right? So oftentimes in this class, you're going to be required to graph, and not just graph eloquently and graph neatly. So you can't graph neatly. It's going to be harder to conceptualize and visualize what the heck is going on with some of these functions, right? And the fact that we're starting off from planes, the most simple one, it's going to be useful to help build your skills for graphing more complex functions. After a certain point, though, you're not going to really be graphing them per se. You're going to be more or less looking at Desmos or GeoGebra or whatever graphing calculator you might use. But it's so important to understand like how to graph them and like understand the shape that it makes. And it relates to other topics as well, like partial derivatives and the gradient and tangent planes, right? We're going to get into that later in this chapter, but it's still important to know. For part B, let's start by getting our coordinate axis out and up. I just like to draw it like this, have my positive x and y look a little bit bigger than my negatives, just because that's the way I like to roll. And I'm going to use blue actually to highlight everything. So we're going to go out and see where it intersects these coordinate axes. So when y and z are 0, x is going to be 1, 2, 3. So I'm going to dot this in blue. When y and x and z are 0, y is going to be -2. And this should actually be, this should actually be a negative y. Oops, that's a bit of a miss. And this should be a negative z down here. And this should be green like that. And now we can actually connect these points across. And then we have x and y equals 0. What is z? So we get that to -6. Pull out that point right there. Oh, that's not the best. Even on an iPad, it's a little bit tricky to graph these sorts of functions. Not these functions, but these planes, even the most simple ones, right? And then you can just shade from here. And that's how you would do part B. Part C is describe the sets of points at which which Q intersects the YZ plane, XZ plane, and the XY plane. So, in fact, actually, this is actually a perfect opportunity to bring this up. If we're looking at specific planes, right, we would say that we were going to hold X, Y, or Z constant. And let's just start off with holding Z constant, right? So if we just said that Z equals 0, we now have 2x minus 3y equals 6. We can rearrange this to get what we really want, 2, right? Let me just double check if that's right. Yeah. So our point starts down here, and then you need to get to 6 tick marks. 1, 2, 3, 4, 5, 6 tick marks to get across, right? And this is the x, y plane, like looking down, straight down on the xy plane. We're just saying that z equals 0, and we're just looking at it like that, right? That's actually like a really good visualization example. If you're ever confused on something, you just set one of the variables to be constant, right? X, Y, or Z, and you get it down to a line, you get it down to a simpler curve, and you understand it. And that's actually part of how partial derivatives work as well. You hold, instead of holding a number constant, you hold a variable constant, X, Y, or Z, right? And yeah, but going back to the actual problem, this one's pretty straightforward because we actually went over it in part B. We just covered it. So it's just going to be this for the XY plane. The XZ plane is going to be 0, -2, 0, and then 0, 0, -6. Yep, perfect. And then we get into a technical definition again. Parallel and orthogonal planes. If you remember from algebra, if you have parallel lines, your slopes are going to be the same. But how does that work in 3D? Well, in fact, you can still have parallel planes. It's just that your d value is going to be different, right? So like, for example, we could have like something like x plus y plus z equals 9, x plus y plus z equals 11. These are never going to intersect. It could also just be like 2x plus 2y plus 2z equals 26. Also will never intersect. And this is also another way we can highlight the scale factor, right? We could divide everything by 2 here. We still get x plus y plus z equals 13. Again, these will never intersect because they have the same normal vector, but they do not have the same d value. And that d value changes everything with respect to this, right? And that means they can't be parallel. Orthogonal, this is something we've covered extensively throughout chapter 11. Take the dot product of the two vectors, and then if it equals 0, then they're orthogonal, right? And this is going to be a fun little challenge for you guys. I already have all the answers down, so if you want to double check, feel free. And yeah, feel free to pause the video. Let's get right into it. All right, so S and T are going to be orthogonal. Are orth because scale factor of, and then Q and R are orthogonal because of a scale factor of -2, and then QS are, oh no, not orthogonal. Oops, this should be parallel. Jeez. Is a scale factor of, not scale factor, oops, no, because dot product is 0, and we can just check with these vectors right here, right? So it's going to be 2 times 6 is 12, -24, 12, goes all the way to 0. And we can try for this one too. We can say that this is 9, this is going to be 18, -18. This is going to be 9, so it's going to go all the way to 0 also. And lining them up is probably the easiest way to do it, so it just saves you some time, right? And that's like the quick shortcut to know. So always look at your A, B, and C components to look for if the two planes are orthogonal, and then look at just lining them up like this, add them up, find out your dot product. Example 5, this isn't a lot of space, but I hope you can still try this on your own. To solve for the equation of a plane Q that passes through this point and parallel to the plane, feel free to pause the video to try this on your own. Let's jump right into it. So we know our normal vector is going to be 3, -2, 1. We know our point, so we'll just do this. Not z, oops. Plus 1 times z minus 1 equals 0. 3x plus 6 minus 2y plus 8 plus z minus 1 equals 0. 3x minus 2y plus z equals -13. Actually, yeah, -13. Perfect. Now this one's going to be more of the brunt of the task out of all the ones we've done so far. And we want to find a line of intersection of these planes, Q and R, and a line in 3D. We can't use X, Y, and Z because that would get us a plane, but we can use a different definition of parametrics, right? And that's the biggest hint that I will give you to try and solve this problem on your own. And if you want to, feel free to pause the video. If not, it's all right. Let's jump right into it. We got our, just get our normal vectors real quick. And then let's just get our cross product ready and good to go. It's gonna be 1, 2, and 1. 2 2, 1, negative 1. And then we will get negative 2, negative 3 I hat, minus negative 1, minus 3. It's going to be plus 3 j hat, minus 3 k hat. We can rewrite this as negative 3, 3, 3, like this. And we can just do a scale factor like we did earlier and above. So now we have our normal vector. And then we can solve for a point in space that would allow us to get something, right? So let's just say z equals 0, because in my head I always like to work with x and y. It's more familiar to me. So let's just say that. So we say that set z equal to 0. You get x plus 2y equals 5, and then 2x plus y equals 7. And if z was any number, it would still work. It's just setting z equal to 0 just makes your life a little bit easier and just a little bit more familiar to you, right? So add these up. We don't even want to solve for or do like elimination. We can just do this. We can do 3x plus 3y equals 12, x plus y equals 4. And then we can pick any point from this combination and then work it out for us, right? So we can say that it could be like 2, 2, 3, 1, and so on and so forth. But in this case, choosing 3, 1, I think might be the easiest. And if you want to just solve for it, go right ahead. I mean, 3, 1, 0 does work. Doesn't matter as much, but if you just want to be 100% sure, that's your answer, and go right ahead. And then we get x equals 3 minus t, y equals 1 plus t, and then c equals negative t, and that is the parametric expression that you're looking for. And last but not least, we have this new concept of cylinders, right? In layman's terms, we have cylinders, like circles just scaled up in 3D. So we have like a circle like this, and we have it like this. And this actually meets the calculus definition of a cylinder because you're just scaling these circles up. But if you want the more rigorous definition, it's just given a curve C in a plane P and a line L, not in P. A cylinder is a surface consisting of all lines parallel to L that pass through C. So we have, if we just set X constant, for example, it would just generate this red line right here. But since X isn't constant, it's going to also point out in the x-axis, right? Same thing for this, right? This parabola right here. It's y equals z squared. And if you were to graph it in the yz plane, like this, you would get a parabola like this. But that parabola is pointing out at you, and you're not even realizing it. That's like a cool thing to think about as well, and it's going to actually help a lot with graphing as well. And then this is our last definition, and this is probably the most important thing to take away from this section, is the definition of a trace. When you are graphing 3D functions, having traces is going to make your life so much easier. And in fact, what we kind of did earlier when we just set z equal to 0 and we just got like a line, that is an example of traces in the xy, xz, and yz planes, right? As you can see right here, it's an ellipse, it's a parabola, it's a hyperbola. These are different traces, and it's going to help you sketch these graphs so much more elegantly. And for example 7, sketching these following graphs, sketching the graphs of these cylinders in R cubed. Identify to the axis to which each cylinder is parallel. Let's just get right into it. This is covering some space I don't really like, so let's just move that up. Move that down, actually, save some space for you guys. Let me just get back to my old colors. So let's divide everything by 16. Yeah, so it's gonna be 2, 2. Let's just make this red. So let's just get right into it. And then we get that, and then we can just extend it upward. That was not the best example of that. It shows that even if you've done calculus for a while, these traces aren't always the easiest. And you can kind of see now that this works as a sort of trace of it, right? And in fact, it's going to be parallel in the XY plane because there is no Z here, it's just going straight up. And then for example B, we can invoke the exact same idea where we have y, no, this is going to be negative x, x, y, negative y, z, and negative z. And then we start off at 0, 0. We go, and then we're going to go, let's just set it x equals sine z. And then we just have to go like this. Oh, no, we don't want a line, actually. We want a curve like this, and that curve's actually extending outward at like this, and you can see it kind of faintly how that would work. And say like if you were to set like y constant or whatever, you would get this, and we can also extend it out in this direction. And the reason why this works is because we're not specifying z, or not specifying y to be anything, excuse me. We're not specifying y to be anything. We're just saying that x has to equal sine z and y can be anything from negative infinity to infinity. And that's why it would extend out infinitely in the y direction. And that is pretty much it. Thank you much for watching. This is part 1 of 12.1. And the next part will be posted very, very soon. Thank you so much.